Good morning. We're continuing our examination of section 6.3, critical points in extrema, and the question is, once we have a critical point, how do we tell whether it's a minimum or a maximum or neither? The easiest way, and I'm going to look at a simpler function, if I have x squared plus 2xy plus 3y squared, is just to look at a picture and see that this is clearly a minimum. What concerns us, however, is if I change b to an appropriate negative number, we can see that we have an image that in the x direction it's a minimum and in the y direction it's a minimum, but I can rotate through to a different angle and find it's a maximum if I look at it from on top going across that way. So simply knowing what happens in the x direction and what happens in the y direction isn't going to be good enough for us. We want something that will let us know that here we have x and y direction are both minimums, and this is what's called a saddle point because it goes both up and down. And if I make that middle term something else, I get one where the x and the y, those directions haven't changed, but what's happened in between has, so this is in fact a minimum. So we're going to look at some algebraic things to understand what's going on. In terms of what we do algebraically, we're going to want to find second partial derivatives. That's where we take the derivative of a derivative with respect to one variable or another. So I'm going to look at my function. My function was x squared plus 2xy plus 3y squared. And I'm going to look at that as f of xy equals ax squared plus bxy plus cy squared. I can compute the partial of f with respect to x. This is x is a variable, y is a constant. That's 2ax plus by plus 0. And the second partial, the derivative with respect to x and x again, I take the derivative up above and I get 2a, and the by is 0, so that finishes it. If I look at f of xy, that's going to be simply b. F of y is going to be bx plus 2cy, and f of yy is going to be 2c. We're going to use something called a discriminant. D equals fxx fyy minus fxy squared, and look at whether that's positive or negative. In the case we had looked at earlier, we see that the second partial with respect to x is positive, the second partial with respect to y is positive, the discriminant is positive. These two are the same sign, that makes the discriminant positive. This is positive, so it acts like we have a positive second derivative in all directions. That's going to be a minimum. But again, notice what happens as I change b, and if I make b negative enough, now my discriminant is negative, and when my discriminant became negative, that's when this other side was going down. So if the discriminant is negative, that's like having a maximum in one direction and a minimum in the other direction, even if they're not both on the axis. Notice I have a minimum in the blue direction and a maximum in the x direction. That's going to be a saddle point. Let's make it so that I can get it exactly 0. And exactly 0 Then we have a parabola in one direction and a line in the other direction. And so in that case, it's going to fail. I don't know whether it's a maximum, minimum, or something else. The test fails when the second partial when the discriminant is 0. Again, we needed to find a place where the first derivatives are both 0, so that gave us a candidate point. So the two ways we have of looking at a function, we find a critical point, so the tangent line in both x and y direction are flat. We can then, if we can look at a graph, we can look at a graph and see from the graph, is this something that looks like a cup, so that it's either a maximum or minimum, or something that looks like it's going both up and down, it's a saddle. We can do that by looking at a graph. If we want to do it algebraically, we take the second partial derivatives with respect to both x, the mixed partial with respect to x and y, and the second partial with respect to y, compute this discriminant. If the discriminant is positive, that means we have either a maximum or a minimum, and we look at the second partial with respect to x to see whether it's a maximum or minimum. If the discriminant turns out to be negative, we know we have a saddle point. If the discriminant is 0, we don't know what's going on. So this lets us test whether or not critical points are maximums, minimums, or extrema. One of the reasons for using the discriminant method is if we're working with functions of more than 2 variables, the discriminant approach generalizes to work with functions of more than 2 variables, while looking at the graph doesn't work with more than 2 variables. So we need to know the discriminant if you go on and are looking at functions of several variables, not just 2 variables.